Hello guys, welcome to my channel DataChaps, where we learn data together. In today's video, we are going to learn about linear regression. So we are going to learn about that using a project called core price prediction. So first we will have some theory and then do a practical example in Python for predicting the car price using linear regression, and then I will also tell you some interview questions, most asked interview questions in this one. So the theory part, I will start with some theory first, and as we go towards the video, then we can have theory as and when needed. So let's get started. So the data set which I'm going to look at it is this data set here. I have the car price data set. I downloaded this data set from Kaggle website. This particular data set has got 10,000 rows. What it has is the features, brand, model, year, engine size, fuel type, transmission, mileage, and the number of doors, owner count. Based on these features, we have to predict the price of the car. So the price is going to be a target variable. All of this is all of these are features. So for example, for a Kia Rio for model 2020, engine size 4.2, fuel type diesel, manual transmission, so on. So mileage, the price is 8,501, and so on. So in this video, we are going to look at how we can handle these text values here. As we know, machine learning will only understand the numbers, but there are some text values here. So how we are going to convert them into numeric fields, and then scaling as well. Let's get started with our theory part, right? So for theory part, I have here, so we are going to learn about linear regression. So when we say regression, we are trying to predict a continuous value. Continuous value is something like temperature, house price, or car price in this case, where there is no fixed value. The value can range anything between $1 to $1 million, or even higher. So anything in this range. So that's a continuous value. And what we mean by linear regression is linear means a straight line. So this is what our linear regression will model will look like. So these are our x features, this is a y predict value. As long as the x is increasing, the y will keep increasing. So that is the basic assumption of the linear regression. So this is a frequent question you might face in your interviews as well. If you're appearing for interviews, then they will ask you what are the assumptions of linear regression. This is the very first assumption, that there is a linearity, a linear relation between your features and the target. As x is increasing, y value is increasing. For example, let's say on the x I have a plot area, and on the y I have price, the house price basically, or just the plot price. So as long as the plot area is increasing, the price will keep increasing. That is a basic thing to know. As long as the plot area is increasing, the price will keep increasing. So there is a linearity here, and it can go the other way as well. For example, we have a price on the y-axis. On the x-axis I have crime rate for that particular area. So in this case, as the crime rate is increasing, the price of the house will increase? No, it will decrease. So in this case, you will have a linear model like this one coming from the other way. So as the crime rate keeps increasing, the house price will keep decreasing. So in both these cases, there is what we call a linear relation, a continuous value. It is keep on increasing. In contrast, if we take another example, let's say we are predicting the human height by their age. So we have age here, I have height here. So age, we can say 0.5 meter, 1 meter, 1.5 meter, and in the age we can have 10, 20, 30, 40. So as the age is increasing, so at 10 years age, 10 years of age, let's say a child is between 0.5 to 1 meter, and at 20 they will keep growing, they will keep growing, they will keep growing. But about at 20, 25 years of age, people will start growing in height. The height will become parallel. I mean, the height will stop growing. So there is no linearity here. So if we draw a linear line here, it will go straight like this one. So at 90 years of age, at the age 90, your linear regression model is actually predicting your height to be maybe 5 meters or 6 meters, which is not true, because after 20 years, they will people will stop growing in height. So in scenarios like this one, linear regression model is not your option. You have to choose a different algorithm, maybe like lasso regression or least regression, which will add a penalty term to the error and then bring it down. So we can discuss about that separately. But this is the intuition of the linear model. So linear regression model will assume that there is a linear relation between them, right? That is the first assumption. And linear relation. And number two, the most important thing is no multicollinearity. So there is no multicollinearity. What it means is the features themselves are not correlated to each other. Like increasing one feature should not increase another feature. So one classic example of this one is the Californian housing data set, which you have in SQL data sets. There are two columns called average bedrooms and average rooms. Right, this average rooms is already taking this average bedrooms into account. So if the average bedrooms is 2, the average rooms is like 4 with hall and kitchen. So if the average bedrooms is 5, then it will be 7 or 8, maybe, if you have something like a conservatory or something. If it is 10, then it could be 12 or 13. So as this is increasing, this will also keep increasing. So this is called correlation between the features. They are positively correlated. So we don't want this sort of a correlation between our features. So that is one more thing we have to keep in mind. There is no correlation between the features. So if you run into a situation like this, then you might want to delete one of these columns. So I would use, if I was asked to delete, I will delete the average bedrooms, because this average rooms is already accounting for this one. Then I will delete this average bedrooms and keep the average rooms. So that's called feature engineering, where you choose the most relevant features, right? And there are some other assumptions which I will create a separate video in the interest of keeping this video short and concentrating on the practicality of this one. So without wasting time, we'll go into our Python code. Okay, this is our data set. Cool. Okay, let's create a new Python file, new notebook. Create a new notebook. I will name it as our price prediction. Okay. Okay. Let me add a title here. So you can create a markdown file here, and then if you add single hash, okay. So what are the things which we are going to do here? So number one, we are going to import all the dependencies. Number two, read the data into data frame. This is the pandas data frame. And number three, we'll do some exploratory data analysis. Okay. Number four, we will do encodings. I will talk about this encodings in a while, and when we come to that point. And finally, fit and predict. Okay, before this fitting and prediction, we will do scaling as well because our numbers are in different scales. And finally, fit and predict. Okay, fit and predict. Let's start with importing the dependencies. The very first thing I want to do is import pandas as PD, and from sklearn dot model selection import train test split. This is the most important thing, to split your data into training data and testing data. This is sklearn, and from sklearn dot pre-processing. So we'll also do a pre-processing step here, like I said, the scaling and stuff. So pre-processing import standard scaler. And what else do we need? We need the linear regression model. So linear regression model comes from linear model. That's linear model have linear regression. Okay, we got the most basic imports we need. Now let's try and read the data into our pandas data frame. Okay, so car data we are trying to read, which is pd dot read csv, is the function which we will be using. So where is my file? My file is one folder up. This one, it is in the same folder. So I can do dot slash dataset slash car underscore price underscore dataset dot csv. Okay, car underscore data. Let's just print this one. Right, I got the data in my pandas data frame here. So like I said, we'll do some exploratory data analysis on this one. The first thing which we want to do is car underscore data dot info. This will give you all the information about the data set. So there is brand model, all these column names, and non-null. Non-null, how many rows are there with non-null values? So we are a bit sorted here, like there are no null values, so we don't have to handle any null values in this one. All of them are null values. And car underscore data dot describe. So when we describe the data set, it will give us the count, mean, standard deviation, minimum, maximum values on this one. And do observe that it will only give these values for numerical fields. You see here, whatever there is int or float, we got the statistics for them, but not for the objects or string values. Okay, we'll find out if there are any outliers. So for that one, I will use Seaborn, right? So I will import Seaborn as SNS. So Seaborn is used for graphical visualization, where we can draw some graphs and visualize the data. One most popular thing graph which I want to use is this SNS dot box plot, to see if there are any outliers. SNS dot box plot of car underscore data. This work. Yes. So if you see, this is the one. So forget about the pricing for now, because that is our target variable, which we are not bothered about that. This is the box plot, or you can have box plot for individual ones. Let's say mileage. Mileage. Right. What do we look for this in this one? So that's our median. that is our q1, that is our q3, and this is the upper limit and this is the lower limit. Luckily we don't have any outliers in this one, but if there are any outliers you will see those points here beyond this line. So this is how you can see the outliers. This is how we can identify outliers using the Seaborn box plot here. So let's not worry too much about that. We'll quickly jump onto the encoding suite. So you can repeat the same thing for all of them. You can use pair plots, you can use count plots, all other stuff. But this is not a Seaborn tutorial, so I'm not going deep into that one. And then the encodings. What are the encodings? So basically, if you see here, if you see our data set here, this brand, model, fuel type, transmission, these four columns are text fields. So machine learning is not good at working with the text fields. We need to convert them into numerical fields. There are a couple of ways where we can do that one. I will tell you what they are. Let's go back to that theory part again. Okay. So imagine you have this data set here, ID and color. 1 is red, 2 is blue, 3 is green, for example. So the methods which we are looking at is one hot encoding, two is label encoding, and there are other encoders as well, like hash encoding and stuff, but these two are the ones we'll be concentrating for now. So what does this one hot encoding do is it will add more columns to your data set by converting these into each of those columns. So when you use one hot encoding, the resulting data set will look like this: ID, color underscore red, color underscore blue, color underscore green. So we have IDs here. So the color underscore the color for ID1 is red, so it will add 1 here and 0 to all others. So basically this is converting this one into binary values. Okay, and for ID2 the color is blue, so it will add 1 here, it will add zeros. And for color ID3 the color is green, so it will add 1 here and 0 to others. So this is what one hot encoding does. If you have like 50 colors like this one, then it will add 50 unique colors, then it will add 50 columns like that. So there are two disadvantages with this one by using one hot encoding. Number one is dimensionality curse. Dimensionality curse. So usually in machine learning stuff, we want to reduce the number of dimensions, we want to reduce the number of features. That's why we do all this sort of feature engineering or PCA, principal component analysis, to identify the most important features. And if you have like 200 features, we will only take the most important features, which will come down to maybe 140 or 150 or even less, to reduce the dimensions, so machine learning model can work faster with less number of dimensions. That's why we use this one. But in this case, with the one hot encoding, we are actually increasing the dimensions. So that is one thing. And how many features are too many? How many features are too many features? How many dimensions are too many dimensions? Well, there is no specified rule on this one. It's down to your model performance. If your model is taking a longer time to compile, then you might want to look at other encoding features. But as long as your model is compiling and predicting correctly and there is a good accuracy score, then I don't think you should really worry about the number of features here, right? And number two, the first one is the dimensionality curve. What's number two? Okay, I just lost track of that. I will come back to this one. And then the second one is label encoding. So what label encoding does is the same data set. I will take the same data set, ID and color. I have one red, two green, and three blue. So if you have for another blue here, for example, then it might assign one to this, two to this one, three to blue, and because this is blue, it will again assign three. Right? This is what label encoding does. So it will still have the same column, but it will convert the values into a unique numerical values. The problem with this one is because machine learning models are working against the numbers, are working along with the numbers, what this will think is, okay, 2 is greater than 1, so green is superior to red and blue is superior to green and red because the number for blue is 3, so this is higher, which in reality it is not categorized in that way. It's just the colors. There is no categorization like that. If you take for example, this is high school, degree, post graduation, and this is also post graduation. So in this case, there is a superiority. Yes, degree is definitely greater than high school, and post graduation is definitely greater than this degree or undergraduation and high school. So in this case, it works well. But when it is a categorical value like red, blue, and green, where there is no ordinal representation, then this is true. So it might work in some algorithms, but when it comes to decision trees, where it is creating multiple trees like this one, and it is saying like, okay, is the color greater than 3, then the decision is completely changing here, although this has nothing to do with the superiority, right? That is one downside of the label encoding. So you can definitely think about this, explore the options, and choose the best one for your case. So in our case, I'm going to go ahead with the uh, one hot encoding. Let's see how it will look. Before that one, I want to see what are the unique values in this one. So if I'm having to use this for car underscore data dot brand dot unique, will give us all the unique values. That's capital B. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So if I use one hot encoding on this brand, it will add 10 more dimensions to this. Okay, I will print out the shape here for our future reference. Let's take the car underscore data dot shape. So there are 10,000 records which you know, and there are 10 columns. So I'm going to apply this one hot encoding onto this one. So there is a way where we can do one hot encoding. It's simply pd.getDummies. Either you can use from the pre-processing, we can use one hot encoder, or we can just use the pd.getDummies. So I'm just using the getDummies method here, getDummies function. So this will be car underscore data. I'm reassigning that to the same car data, right? So pd dot get underscore dummies. We need to specify the data, which is our car underscore data, and then columns. So you can specify one column or multiple columns here. So I will specify multiple columns because we have multiple of them. So we have brand, we have model, we have what, field type, and there is one more column. What is that column? Transmission, is it? Transmission, right? So transmission, And after this one, if I print car underscore data, oops, close the bracket here, no problem. What's the error? Fuel underscore type, it's fuel underscore. Okay, what's the error here? So have to use the capital T here and run this one and see what happens. Like I said, okay, the column brand is gone, the column model is gone, fuel type and transmission are also gone. Instead, they are converted into brand underscore Audi, false, 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 false. This one brand underscore BMW is true because that's the BMW brand. Rest everything is false. So you might argue why these are true or false. For that one, we have to specify the D type to be int. So when you specify the D type to int, D type is equal to int. What does it say? None of the brands. Okay, these are all already done. So I have to reload the data again. I will run all the cells. Okay. Now there are zeros and one, like how I showed you on the theory part. So we got all of them down. Let's if you look at the shape here, it's now 53 columns. So from 10 it went to 53, so we have increased 43 columns, which is not a major concern for me at this point of time, because uh, we'll see how it goes as we go further, if our model is performing well or not. And then we should use the scaling part, right? So before the scaling part, I want to convert this data into train test split. Let me add a markdown and train test split. So remember that you should apply scaling only on the training data, not on the testing data. You can transform on the test data, but you can't fit on the test data because it will cause a data leak, and your model will tend to memorize the values. Okay, so in order to do the train test split, I have to split into x and y. X are my features, which is car underscore data, everything except the price. So I'm dropping price here, and x is equal to 1. So when we specify axis, I'm asking the data frame to drop the column. If axis is 0, it will drop the row, right? And then y, my y is car underscore data dot price, symbols. So we got this one. Let's see the x dot shape comma y dot shape. So in x there are 52 columns, which is true. Previously it was 53, but ignoring the price column, there is 52. On y dot shape there is only 1. Okay, now the train test split part. So we are going to use the train test split function from sklearn metrics, scikit-learn library, which we have already imported up there. So when we use that function, we get 4 parameters out. So x underscore train, x underscore test, y underscore train, y underscore test is equal to train underscore test underscore split. I have to pass in the x, I have to pass in the y, and then we can specify the test size. Test size, I will specify that to be 20%. So 0.2 is 20% for testing, and the rest is for training data. And then uh, we can or we cannot specify. It's up to us. Random set. This is for reproducibility. So if I run this command without this random state, every time my train and test will tend to change. It will be random. But when I set the random state to true, even if I run this statement a million times, I will get the exact same set of train and test data. So this is important when you are trying to use the reproducibility. Okay. Um, okay, so we got this x underscore test. I will just print the shapes of each of them. X underscore train dot shape, comma x underscore test dot shape, comma y underscore train dot shape, comma y underscore test dot shape. Because I said 20% is my testing data, then 8,000 went into this training and 2,000 went into testing. The features are the same for both of them, and again 8,000 for training and 8 for testing. So if I specify this to 4, then we will see 6,000 going into training and 4,000 going into testing. Okay, I will settle down with this 0.2, so 20%. Now that we got the training and testing data, we have to scale the data. So what is scaling? Basically, if we look at this one, the years are in the range of 2020, 2001, 2005. The engine size is 4.2, 2.0. Mileage is in hundreds of thousands. This is 289,000. Doors are in 3R5. So there are different scales, which is not ideal for our model. Our model wants everything to be in the same scale. So go back to theory now again and see how this scaling works. Scaling. So imagine if someone is telling you what is the price of a pen, that is $1.32, and what is the price of the pencil? They are saying 190 cents. So these are two different scales. Basically, we want everything to be in one scale. So if you are given like a thousand prices like this one, or thousand prices, at some point you might get confused with between the dollars and cents. Instead, if they are both converted into, instead of this one 1.90, if I said 190 cents, if I said 1.90, it makes us easy. It makes it easier for us to calculate them. Otherwise, at some point we'll get confused. The same thing happens with our machine learning models as well. So if something is in scale 1, 2, 3, 4, 1, 2, 3, 4, it goes like this. But if it is something is in scale again 1, 2, 3, 4, and something is in like 2,000, 3,000, the line is a data point is here. For something, a data point is here on this one. Then these data points are too far away on the hyperplane. It makes it really difficult for the machine learning model to do that one. So it's like we help the machine will help us in turn. So the help the machine is expecting from us is bring all the data into a standard scale. And for scaling, there are a few techniques. One is standard scaler. Number two, min max scaler. So there are other scalars as well, but these are the two most popular ones we use mostly. So this standard scalar is also called as standardization. This min-max scalar is called normalization. So I will give you a really simple example on what this is. So if you have data from 0 to 100, and if I have a data point here at 30 and a data point at 40, right? And I have the exact same thing. Oops. So I have 0 here, I have 100 here, I have a data point at 20, I have a data point at 70. So what this normalization, this min-max scalar does is, so I'm talking about min-max scalar. min-max scaler will convert all the values between the range of 0 and 1. So in this case, this 20 could become 0.2 and this 70 could become 0.7. So these are the basic examples I'm giving. So it may not be exactly the same, but that's how it scales the value. And in the on the other hand, what the standard scaler does is, when you have a 0 between 0 and 1, when you have a 20 here, when you have a 70 here, it will bring the values with having a mean of 0 and standard deviation of 1. So with the calculation, it is a bit hard to see how these values will be scaled, but it will bring the values with a mean of 0 and standard deviation of 1. So the values can range anything between -1 and 1 or -3 and 3 as well. But instead of having like 2000 or 5000 value, 2000 or 5000 values, smaller values like this one is much better for the machine learning model to work with. So that's what we are going to do now. Let's see how this standard scaling works. So for this one, for the scaling, if you have seen my imports up here, I've imported standard scaler from the pre-processing. That is the exact thing which we are going to use here. The first thing we have to do is declare a variable for standard scaler. Okay, I got the standard scaler here. Now scaler dot fit. So this scaler has a fit, a transform, a fit and transform, fit and transform. So you can transform that and fit that, or you can fit it separately, or you can fit and transform at the same time. So it's your choice. So what I will do is I will use the fit and transform on x underscore train. So remember, I told you that we should only fit the scalars on the training data. You should never ever fit the scalar on test data, because it will cause a data leak and your model performance will be bad, of course. So what it returns is, it returns another ND array. So I will assign that to the same variable, or let me take another variable, x train scaled. And what about the x test? So x test scale is equal to scalar dot. Remember, we should only use transform. We should not fit that. Okay, x underscore test. Shall we see the x underscore train now? X underscore train underscore scaled. So if you see, the values have reduced. So we have a slight problem here, which I've just observed. So you see our encoded values, one hot encoding, brand Audi, brand BMW, we have already scaled them. They are binary values 0 and 1. But because I have specified train on the entire fit and scalar on the entire train set, then it transformed those values as well, the zeros and ones basically, which are one hot encoding. I don't want that to happen, so I will fit scalar only on specific columns. For that one, features to scale. So what are the features I want to scale? The first thing I want to scale is year. Okay, and then brand, no, not brand, engine size, and then mileage, and then doors, and owner underscore count. So these doors and owner underscore count, maybe they are not necessary to scale them, because they're already low numbers, like owner count maximum I've seen 5, I think. The doors also maximum 5 doors. It may not be necessary to do that one, but I'm just doing that for now. Let's see if there is any problem with the predictions or something, then I will come back to this and to it, right? And so instead of scaling all the features, I will use this one here, and then only scale these features and only scale these features. Owner underscore count, this capital letters are killing me. Okay, so what is the shape of this one? Did it reduce the features? It did reduce the features. It did reduce the features. Scalar underscore train. Just update this one itself. Scalar dot fit transform x underscore train. Features to scale. Features to scale. What is the shape? Scale 5. 5, 1, 2, 3, 4, 5. Okay. Let's just use them normally. I will post an update on this one. Why it's not happening? So now I'll scale all the features and how it goes. Okay, 52. So we have scaled this one. Now finally the model fit and predict. So again, if you see, I've imported the linear regression there, and then model dot fit. What are we trying to fit? The x underscore train underscore scaled, comma y underscore train, which are my labels or predicted values. So that has fit. Let's check the score. So a model has every algorithm will have a function called score. So we can use x underscore train underscore scaled, comma y underscore train. So we got 99.91% accuracy. So just to make sure that this is not overfitting, that means it is not performing well only on the training data. I want to check that on the test data as well. So test scale and y underscore test. Okay, on the training data as well, it's fair enough. It's got 99% accuracy. So our model is performing really well here. So this score, talking about this score, every algorithm, like I said, every algorithm has a function called score, which will return the accuracy score for you. Otherwise, there are some metrics provided by scale-learn.metrics. You can have accuracy score here, mean absolute error, mean squared error, root mean squared error. I will create a separate video on that one, how to use those metrics from sklearn, but for this video this is all I have. So just to summarize what we have done so far, we have imported all the dependencies, loaded the data into pandas data frame. These are our features. The price is our target value. We've done some basic exploration on how the data is looking like, and this is how you can see the outliers using the box plot. And then the unique values, because these unique values are not a lot in brand or model. I've just done one hot encoding using get dummies, and then uh, separate the x and y, basically the features and target, and then train to split, and then scaling. I've used standard scalars here. Now you should know the difference between the standard scalar and the min max scalar as well. And we have applied scale. We have fit the scale on train data, transformed on the test data. Finally, we have taken the linear regression model, fit, and predict the score. That's all I have this video. In the next video, I will do a logistic regression model. I'll see you there. Bye bye.